On this channel, we provide useful programming information with practical code examples. This time, it's about the threading module in Python. You can learn the basics of threads in Python, thread synchronization, daemonization, and other practical points with code samples. Enabling subtitles will make the code descriptions easier to understand. The threading module in Python is a standard library that supports multi-threading programming. Using threads allows multiple processes to run concurrently, which can improve the performance of programs, especially in cases involving blocking operations like I/O waits. Due to Python's global interpreter lock, GIL, the effectiveness of multi-threading is limited for CPU-bound operations, but it works efficiently for I/O-bound operations. The following sections explain the basics of using the threading module and how to control threads. To create a thread and perform concurrent processing, use the threading thread class. Specify the target function to create a thread and execute that thread. In this example, the worker function is executed in a separate thread, while the main thread continues to operate. By calling the join method, the main thread waits for the subthread to complete. Giving threads meaningful names makes logging and debugging easier. You can specify it with the name argument. Threading enumerate returns a list of current threads, which is useful for debugging and monitoring state. If you want to customize the thread executing class, you can define a new class by inheriting the threading thread class. In this example, the run method is overridden to define the thread's behavior, allowing each thread to maintain its own data. This is useful when threads perform complex processing or when you want each thread to have its own independent data. When multiple threads access shared resources simultaneously, data races may occur. To prevent this, the threading module provides several synchronization mechanisms. The lock object is used to implement exclusive control of resources between threads. While one thread locks a resource, other threads cannot access that resource. In this example, 5 threads access a shared resource, but the lock is used to prevent multiple threads from modifying the data simultaneously. If the same thread needs to acquire a lock multiple times, use an RLock Reentrant lock. This is useful for recursive calls or for library calls that might acquire locks across different calls. With RLock, the same thread can reacquire a lock it already holds, which helps prevent deadlocks in nested lock acquisition. Condition is used for threads to wait until a specific condition is met. When a thread satisfies a condition, you can call notify to notify another thread, or notify_all to notify all waiting threads. Below is an example of a producer and consumer using a condition. This code uses a condition to have the producer notify when data is added, and the consumer waits for that notification before retrieving the data, achieving synchronization. Daemon threads are forcibly terminated when the main thread ends. While normal threads must wait to terminate, daemon threads terminate automatically. In this example, the worker thread is demonized, so it is forcibly terminated when the main thread ends. Apart from the threading module, you can use the ThreadPoolExecutor from the concurrent futures module to manage a pool of threads and execute tasks in parallel. ThreadPoolExecutor creates a thread pool and efficiently processes tasks. Specify the number of threads to run concurrently with max_workers. Using threading event, you can set flags between threads to notify other threads about the occurrence of an event. This code demonstrates a mechanism where the worker thread waits for the event signal and resumes processing when the main thread calls event.set. When exceptions occur in threads, they are not directly propagated to the main thread, so a pattern is needed to capture and share exceptions. By putting exceptions into a queue and retrieving them in the main thread, you can reliably detect failures. If you use concurrent futures ThreadPoolExecutor, exceptions are rethrown with future result, making them easier to handle. Due to the mechanism of the GIL global interpreter lock in CPython, multiple Python bytecodes do not actually run simultaneously within the same process. For tasks that are CPU-intensive, such as heavy computations, it is recommended to use multiprocessing. On the other hand, for I/O-bound tasks such as file reading or network communication, threading works effectively. Using Python's threading module, you can implement multi-threaded programs and execute multiple processes concurrently. With synchronization mechanisms like lock and condition, you can safely access shared resources and perform complex synchronization. In addition, using daemon threads or ThreadPoolExecutor, thread management and efficient parallel processing become easier. The source code for this video can be downloaded from the official website. If you like, please visit the URL in the description to aid your learning. Thank you for watching. Subscribe to the channel and check out our new videos.